In this video, I'm going to go over electric actuated individual blade control, also abbreviated swash plateless rotor system, or active rotor control is also a commonly used term. The incentive for using this technology are twofold: a reduction in mechanical complexity, as the swash plate and necessary hydraulic systems, hydraulic booster, hydraulic pump, hydraulic relay, hydraulic lines, as well as individual servos located underneath the swash plate, entail and bring with it a significant degree of mechanical complexity, which reduces the reliability of the system and hence increases the maintenance cost as well as likelihood of failure. Now, electronic rotor control is a relatively new phenomenon. It has not, while independent rotor control has been studied for an extensive period of time, over 40 years. It was actually invented by Norman Ham at Massachusetts Institute of Technology. It has not ever really gained any kind of momentum, primarily two reasons. The industry is very conservative on anything radical. This is considered radical, right? You're getting rid of the entire hydraulic system of the aircraft and replacing that with electric actuators located on the rotating assembly, and then you have to get current to those motors, and you have to ensure that transmission of current is as reliable as the mechanical transmission of hydraulic energy, right? Because what you're doing is all of the critical systems, the actuation energy propulsion system, is all safely stored on the stationary portion of the aircraft. And the rotating assembly obviously is more prone to failure. I mean, you have more vibration, you have the rotation exposed to the elements, it's exposed to a high rate of airflow, it's exposed to a large amount of potentially the aircraft's operating in the rain. And so it's obviously exposed to the elements to a much greater degree than these hydraulic systems nested safely away in the fuselage. And so that's a common critique. And again, the most common critique is the safe transmission, reliable transmission of some type of power. So that could be hydraulic fluid via hydraulic slip ring, or most likely electronic power, since we want to use electric actuators. Now, so let me ask you, why use electric actuators? Well, it's simplicity, right? The actuators have a very high power density, has increased tremendously over the years, and there's an increasing trend in a multitude of areas to increasingly use electric actuation systems rather than hydraulics. That has been a trend that's been increasing, and the main limitation has always been getting the necessary mechanical power, because an electric motor can really only produce so much power as opposed to a hydraulic actuator, and that is going to remain the case, but nonetheless the electric actuators have gotten to the point where they're sufficiently capable and sufficiently power dense, compact, and reliable to meet the requirements, the very strenuous requirements, very critical requirements that is found in main rotor actuation. Now, there's a simple way to transmit electrical power to the rotating assembly, and that is by locating the generator on the rotating assembly and passing a shaft that would otherwise spin the generator to the fixed assembly. And that, in this case, is a rather unorthodox setup because our main rotor is powered by electric motors. One may ask, why would you do that? Well, that's because that's related to a separate innovation we'll go on later. But there is, this is not a new idea. Airbus has a patent on electric main rotor drive. It's not well known, but nonetheless there is interest in doing it because it provides numerous advantages that we'll go over in a separate video. But the point is, we have our axial flux electric motors stacked up, and if you can see, if you're familiar with axial flux motors, you'll notice this configuration where you have these compact discs that are stacked together, and of course you have a hollow section through where our shaft that powers our generator. The shaft actually could be much thinner, and then we have our epicyclic gearbox, because nonetheless we're electric motors, depending on the power density and the RPM found, the RPM of that motor, you're going to require a reduction of some degree. In this case, it's about 13 to 1, from 4,000 to about 300 And my father is getting on my nerves. Can you stop Skyping? And I'm making a video. Apologize for that. So this way, as long as the rotor is spinning, the main rotor is spinning, we have electrical power. Now, you may say, well, what about when you are spooling up the aircraft? You'll have an insufficient amount of electrical power because the rotor RPM will be lower. Well, you really don't need to change the pitch of your blades as they're spooling up. They're going to remain fixed. There's little need to spool them to twist the blades when you're spooling up the aircraft. Now, what about during an auto rotation? That is a very good point, and that is going to be the main critique of the system. Well, the actuators will be able to lock at a lower pitch. So if you want to maintain a minimum pitch when you are descending into an auto rotation, you want to keep your pitch as minimum possible so the rotor speed up, and then coming down at the end, you want to pull up pitch. That will be able to be accomplished through the use of an auxiliary slip ring, or you can think of it as a secondary slip ring. So the rotors are not spinning at a sufficient speed to be generating electrical power. You'll be able to provide actuation power. So again, if your rotors are not spinning at the speed that is sufficient to generate sufficient electrical power for the actuators, you will have the ability to transmit electrical power from the stationary to the rotating simply via slip rings. Slip rings are in addition to our main system. This is obviously very redundant. This is just as reliable. Engine's completely, electric motor is a generator, is completely covered from the elements. It is sitting up there spinning, making electricity to power these actuators. Now, these actuators can either be located directly in plane, so they could be, if my cursor right here, you can see we're going to go from here to say here, and place the actuator directly in plane. That does somewhat interfere with the design of the rotor head, and if you have a 4-rotor system, the perfect place is to put them out of the way right here at a 45-degree angle from the plane of the rotor. So then you have a interconnecting system here. Again, they are all independent. So that is the main reason we want to do this. Is that we're no longer interconnecting all 4 rotors together with a swash plate. As you know, we can find a video on EC145 swash plate animation. I have to keep this video under 8 minutes. Right? So, okay. So as you change, this is collective. So if we go to cyclic, right, you're still changing the pitch of more than one blade. It's impossible to change the pitch of a singular blade. It is basically, that's collective. Let's get cyclic. This is collective. Let's try to get cyclic again. So here is cyclic. As you can see, there's more than one blade spinning, which is exactly what you don't want. That's going to create excessive, unnecessary vibrations, which is the primary objective of this rotor system. So one may ask, why go through all this additional hassle? Actually, you're reducing complexity by doing this, but you may ask, why bother? And that's to reduce vibration, increase agility, increase performance, reduce power consumption, as follows. So all these numbers are from peer-reviewed papers, and these are not made up. 5 to 7% reduction in power consumption, 5 decibel or more reduction in sound, especially a very significant reduction in blade vortex interaction, impulsive sound, BVI. IBC provides up to 80% reduction in vibration. Okay, that has been verified multiple times through multiple both wind tunnel testing as well as actual aircraft testing. ZF, the manufacturer of the EC135 gearbox, is in addition to marine transmissions and multitude of transmission products, has designed specialized actuators for these rotor blades. But again, any company in the world that has basic manufacturing capability would be able to design and develop very high power dense actuators, because after all, actuators are not restricted to rotorcraft blade actuation. They can be used in robotics and automobiles and aircraft, and so developing high power dense actuators is something that many people are working on, and so therefore we can apply that technology. And the gains made in electric actuator power density, again, as I mentioned, there's an increasing trend because of the simplicity and reliability of electrical systems to replace anything hydraulic with electric. So if we can do that on specialized robotics or even potentially on some aircraft, aileron control, elevator control, rudder control, all could be potentially electric. Not the propulsion, as many people argue, but maybe the actuation can. So these actuators can be readily manufactured, and minimal modification to the actual rotor head is going to be required. So if we go to, here is the rotor hub for the H160. As you can see, there is enough room to mount the actuator right as my mouse cursor is pointing towards. Inside the actual grip may not be the ideal location. It interferes with the design of the grip. It requires the grip to be, again, potentially enlarged to some degree. It could be argued to be simpler to have it directly in plane, but a design where the actuator is positioned as this is right here would be simpler. Now, is this has any aircraft flown with this technology? Yes. An aircraft, a CH-53 in Germany, a CH-53, don't remember the designation, flew with hydraulic pitch links, right? The technology has never been used on any production aircraft. So it has been purely experimental up to this time, and I foresee it remaining experimental for the foreseeable future, as the industry is very conservative. You imagine, what's the newest rotorcraft certified? Well, it's the Copter SH09, and I've had communications with the founder and designer, and he designed an innovative carbon fiber rotor head that resembled a Bell soft and plain design. So the flex beams, rather than fiberglass or carbon fiber, they eventually abandoned that design and went to a very conventional Leonardo style design. And let's go. So this is the rotor head that is being used on the SH09. Very conventional design, about 30 years old, 40 years old, somewhere there. So the industry is very conservative due to certification requirements, and therefore it is unlikely that this technology will be used on civilian aircraft anytime soon. Now, my company that I've founded, as I should mention, I had come up with this idea back in 2017, and I should actually show you the first drawing. It's quite funny. And I had come up with the idea, suddenly Googled it, and I found some guy on Stack Exchange that asked the question, and then the answer to the question, well, it's not going to work because you have to use slip rings. And I said, well, that's not true. You can place a motor on the rotating assembly and then have a shaft going down connected to the stationary assembly, and then you would provide electrical power as long as the rotors are spinning. I said to myself, logically, it would make no difference in terms of redundancy. Why would it be any less reliable than this complex swash plate system? So, with that said, a 30 to 40-year-old idea, which is quite obvious. I mean, think of anybody, if a 17-year-old could think of it. I said to myself, I'm looking at this rotor head, I'm thinking, why on earth would I want all those stupid pitch links and swash plates? I can just put an electric motor right there and change the pitch. Screw that. And so I went with that, and it turns out that it's going to be a major revolution in rotor technology. It's going to be equal to the development of elastomerics. It's going to be equal to the development of the flex beam by Rini Milieu at Aerospatiale, and I would say it would be comparable, if not even more, than the development of the full rigid flex beam rotor system by MBB in the 1960s. And of course, widely used on the 135, or exclusively used on the 135, now going to be the main rotor system for the 145. So that's a very promising technology, and I think that eventually all helicopters will use this independent rotor control system with electric actuators. And that's about all I have to say.